All right, so all the coupling patterns, the multiplicity that we've seen so far has been relatively simple, but that's not always the case. We can have actually complex coupling patterns that are much harder to decipher. Overall, these will be very rare for this course, and you won't see any kind of NMR spectrum be asked to find out the structure through this complex patterning, but you might be asked some other questions about this complex coupling. So let's take a look at an example where we have kind of HA next to a carbon, and then there's two HBs, right? And then there's just other stuff on these bonds, right? And so we're going to take a look at HA. And right, HA, if it didn't have any neighbors, it would just be a singlet. However, it does have neighbors. And so what we can do is we can draw these tree splitting diagrams. So first off, it couples with HB here and splits the peak in half, right? And the amount that it splits this peak, we call this a J. So we'll call this JAB. And this is what's known as a coupling constant. And so after it gets split by the first J or HB, then it'll get split by the second HB. And since the two HBs are the same, they'll have the same coupling constant. And so when it splits these peaks again, because these coupling constants are the same, the two peaks fuse together. And so what you end up with is a triplet, right? What we've already seen before, where the middle peak is now kind of twice the size because it has two fusing together of the side peaks. However, we can have more complex scenarios. So let's take a look at this compound. And specifically, we're going to take a look at HC here. Right, so if it were by itself, it would just be a singlet, but it does have neighbors. The first thing we have to recognize is that HB and HC are diastereotopic protons, and so they are different from one another. And so what that means is that they will couple with one another. And then we also have HA as well. HA is within 3 bonds of HC, and so it will also couple there. However, these are different types of couplings, right? One is 3 bonds away, one is 2 bonds away, and so their coupling constants here will not be the same. So for example, between HA and HC, the coupling constant is between 11 and 18 hertz. And so this proton will be split, HC will be split by HA into a doublet, and then it will continue to get split by HB. However, this coupling constant is only about 0 to 5 hertz, right? So it's much smaller than the other coupling constant. So call this JAC. And then we're going to split it again, this time by a much smaller amount. Maybe something like that, where this is now JCB. Right, and so what you can see now are 2 peaks in the middle have not fused together, and so we won't get a triplet. What we get is 4 evenly sized peaks. And so what this is referred to is there's 2 doublets, right? There's a doublet here, and then the doublets get split again into doublets. So this is called a doublet of doublets. And so you can tell that this is different from a quartet because here all 4 peaks are approximately the same size, whereas in the quartet, the 2 center peaks would be significantly larger than the other. And so this type of complex coupling can occur whenever you have these alkenes, and then also in some other situations such as chiral carbons. So here's just the NMR spectra of all these, right? J, C, B, and A. You can tell HA looks like 4 approximately evenly sized peaks, right? Those are doublets of doublets. And then HC and HB are also doublets of doublets, right? There's a doublet right here, and then they get split up into 2 tiny doublets as well. And so you can see that the patterns can get quite complex. Again, you won't be shown an NMR spectra with complex pattern and be expected to deduce the structure, but you may be asked kind of, okay, here are the coupling constants, what would it look like type of thing. One of the other issues, especially when we get to these complex peaks, is that many times the peaks will overlap. And it's going to make it too hard to analyze. If you get a higher resolution NMR, then you might be able to differentiate between the peaks. But if you're looking to something, that's lower resolution, it's going to be really hard to do this. And so sometimes when we get this kind of jumbling of peaks, such as what can be seen in this methylbenzene or toluene, we see we have HB, C, and D, and they all show up right in the same kind of region. And so it looks kind of like just a bit of a jumbled mess and hard to determine which one is which. So oftentimes what you'll see is you'll see it just be called a multiplet. Right? Instead of trying to figure out what is that a triplet, doublet, quartet, that kind of thing, we just call it a multiplet. Here's just a picture of some generic coupling constants for different types of protons. You can see over here is what we mostly work with, right? This kind of hydrogens next to each other, 3 bonds away. That's about 6 to 8 hertz. You can tell when you have an aldehyde, you get a very small coupling. And then the cool thing about these alkenes here is that they have different coupling constants based on where the hydrogens are at, right? If the hydrogens are trans to each other, then it will have a very high coupling constants. If they're on the same side of each other, it'll have a somewhat lower coupling constant. And then if they're on the same carbon, right, geminal to each other, will have a very small coupling constant. You can also tell aromatic rings also have some more complex coupling with this. What this is called metacoupling, right? This 4-bond coupling. Again, this will be pretty rare for this class. You won't see any NMR spectra and be expected to deduce these values, but you may be asked other types of questions. So check out the work along problem set, that kind of questions. One thing you might notice is that these are all given in hertz. So how do you take a look at a peak, right? Let's say we have this peak here that's kind of looking like a doublet, and we want to know what is the coupling, right? Remember, these are given in parts per million. So how do we go from parts per million to hertz? And overall, it's really not too bad. All you have to do is identify the peak. So let's say this one is at 4.260 parts per million, and this one is 4.247 parts per million. All you have to do is subtract the values, right, to find the difference between these two peaks. So here we would get 0.013 ppm. And then all you do is you take this number and you multiply by the megahertz of your NMR. Right, so NMRs go from like approximately 70 megahertz to 900 and above. So for example, let's say we had, this was taken on a 500 megahertz NMR. We would simply take this 0.013, multiply it by 500, and get 6.5 hertz. And so, right, you could use this value, say you knew that this was an alkene. What kind of splitting would you have here? Oh, well, you'd say, well, because of the coupling constant is 6.5, we probably have some kind of cis alkene. Again, take a look at the work alongs. We won't see too much of this complex coupling.